Hello friends, so today in this video we are going to solve one question which was asked in GATE 1996. So the question is, a Zener diode works on the principle of, and options are A, tunneling of charge carrier across the junction, B, thermionic emission, C, diffusion of charge carrier across the junction, and D, hopping of charge carrier across the junction. So we know that Zener diode is a special purpose diode which is used in reverse bias direction, right? So we generally use Zener diode for applications such as voltage regulation, right? And Zener diode is always used in reverse bias saturation, and we have very much higher doping to form a Zener diode as compared to normal diode or avalanche diode. Okay, so let me just draw the PN junction, the normal PN junction. So the normal PN junction having p-type material, right? See, p-type layer, I would say. So this is, say, p-type, right? So we have seen in the previous video, PN junction is having, when we make a PN junction or when we add a p-type material to the n-type material, so we'll see a band bending, right? So I'm not going to explain that how this band bending occur, which is in the previous videos. So I'm just going to draw the PN junction. So this is the Fermi level diagram for the PN junction, right? So this is our PN junction. Okay, so here you have, this green is your intrinsic Fermi level, okay. So this is your valence band, this is your conduction band, this is your intrinsic Fermi level, and this is Fermi level of p-type, right? So why this is our p-type, and this is the n-type semiconductor. Similarly for n-type, this is EC, this is EFN, right? And this is EV, this is EFI, intrinsic Fermi level. So here you can see that the EFP is below the EFI. Why? Because we have seen in the p-type material the Fermi level lie below the intrinsic Fermi level. Similarly in n-type material you can see that the Fermi level in in n side is above the intrinsic Fermi level. Okay, so this is the diagram for, or I would say this is the Fermi level bending or the band bending for the PN junction, right? Normal PN junction. So here doping is very less, right? So now what happens in case of higher doping? So let me just draw the PN junction for Zener diode where we have a higher doping, right? So when we doped a material with higher concentration, what happens is the doping concentration is proportional to the built-in potential. So as we increase the doping, the built-in potential increases. Here built-in potential is nothing but the height between p-type and n-type material. So we can say that as we increase the doping, the height will increase. So let me just draw this thing. Okay, so this is under higher doping, right? So this is your Fermi level, right? And this is the Fermi level at the intrinsic Fermi level, right? So let me just again write down everything. So yeah, so here you can see that the gap is, now the gap is this much, gap has increased, E phi p. Okay, so as you can see, this here the doping is say high, right? Doping is very high as compared to the normal diode and the avalanche diode. Okay, so here you can see that the normal PN junction and the Zener diode, the PN or the band bending of the two different diodes. So here you can see that as we increase the doping, the built-in potential also increases. So this is under no bias condition, right? So this is under no bias condition. This is under no bias condition. There is no biasing has applied so far, right? So now we'll make one more figure in for this Zener diode when there is biasing. So we know that Zener diode works in reverse bias. So let me just make another PN junction bending diagram when it is connected to the reverse biasing. So when we connect a Zener diode to reverse biasing, so Zener diode under reverse bias condition, right? This is under reverse bias condition. So let me write it down, reverse bias condition. So this is under reverse bias condition. So here you can see that once we connect a PN junction or a Zener diode to a reverse bias, so the P type, right? So the P type is connected to which polarity? Minus, right? Negative potential, and N is connected to the positive in reverse bias. So here you can see that the P is connected to negative. That means we are supplying more number of electron to the P type. As a result, what happens is the overall Fermi energy, this is the Fermi energy, shifts upward, right? Because we are giving more number of electrons. So as we give more number of electron, as a result, this Fermi level gets more electron, right? And as a result, the overall the Fermi level shifted to the upward direction. Similarly, for the n-type material, we are this n-type is connected to the positive terminal. As a result, we are giving holes, right? Or we are taking out electron from this part. So as a result, what happens is there will be a deficiency of electron, right? Or more number of holes will be present. So as a result, the overall this Fermi level will drop down, will go down, will come down. So here you can see that earlier when there is no biasing, both the Fermi level was lying at the same point, but once we connect it to the reverse bias, so as a P is connected to the negative terminal, which is giving more electron, as a result the overall P region shifted upward, and N is connected to the hole. That means it is taking electron from the N region. So as a result, there is a deficiency of electron. So overall layer or overall P region is going down. This is going up, right? So now here we have in N-type, in conduction band, right? What we have is conduction band. We have free electrons, right? So here, say we have free electrons in conduction band. Right. So the movement of electron from conduction band to the N side to P side is not possible. It is not possible. Why? Because electron cannot move from lower energy to the higher energy. So the movement of electron, because the gap is very high, is not possible from N-type region to the P-type region. But you can see that the conduction band of N side is aligned to the valence band of P side, right? So as a result, what happens is electron from N side instead of going to the conduction band of p side, which is not possible because the higher energy, right, an electron cannot go from lower energy to the higher energy, it is not possible. Electron move from conduction band to the valence band of p side, like this, right? So that way electron move from conduction band to valence band, and they recombine with the holes, right? So they recombine with the holes present in the valence band. So this type of movement, right, so this type of movement is known as tunneling. So this type of movement is known tunneling. So this happened in tunnel diode as well, and in Zener diode as well. So here you can see that the Zener diode works in the tunneling principle, right? So in Zener diode, when we increase the doping, as a result the built-in potential increases, right? So when the built-in potential increases, the barrier, right, the barrier width decreases. So the width of the barrier is very less in Zener diode. So here you can see that the width of the depletion region is very less in case of very less in case of Zener diode, but in case of normal diode the width is quite a bit moderate. This is the p, so this is the normal p-n junction, and this is the Zener diode. So as we increase the doping, the width or the depletion width reduces, right? As we increase the doping, we know that as we increase the doping, the width reduces, right, but the depletion, right, but the built-in potential, which is phi b, increases. So this is the common relationship that we need to understand. So here you can see that as we increase the doping, the built-in potential, which is the height, increases. As a result, this is the barrier potential, right? This is the barrier potential which is reduces, and as the height increases, electron is not capable enough to move from the lower energy level, which is here, right? Electron is not possible to move from lower energy level to this point, lower energy level, to the higher energy level. So what they do is they do tunneling. So electron from conduction band passes to the valence band, the conduction band passes to the valence band of p type through the tunneling effect, and as a result a constant amount of current starts flowing in the Zener diode. Okay, so let's go to the question again. Okay, so here the options were, first was the tunneling of charge carrier across the junction. So the right answer for this question is A. What about the B, the thermionic emission? B is not the right answer. Why? Because thermionic emission occurs in metal semiconductor junction, right? Metal semiconductor junction, because thermionic emission normally occurs in the metal. So in metal semiconductor junction, you can see that phenomena occurs. Similarly, option C is not right, because diffusion of charge carrier across the junctions. So the word diffusion is associated to forward bias, right? So diffusion process normally happens in the forward bias, so it is not also possible. Hopping is also not the right answer. So the right answer for this question would be A. Thank you.